I hope that after the first homework, actually second homework, and the discussion about this homework, you understand better basic notions like p-value, and we continue with discussing more practical example. Particularly, we will discuss today so-called two-sample t-test. Um, and other examples of t-tests. So, what is a two-sample t-test? This is actually a uh, very oftenly used test, and the problem that this test solves is the following. Um, Again, assume that we are interested in some numeric feature of, for example, some people, but this also can be any other objects like words or durations in some text, some anything. So I will discuss something that is easy to imagine. So let us assume that we again are interested in the comparing between, for example, we are interested in, is it true that people in St. Petersburg are taller than people in Moscow? So we have the research question like, is it true that people in Moscow, that people in St. Petersburg are taller than people in Moscow? Uh, so I believe it is possible to imagine some legitimate research that can be interested in this kind of question. For example, probably I assume that under that, for example, in St. Petersburg, the weather is more is less warm than in Moscow, and it probably due to some evolutionary reasons lead to the fact that people in St. Petersburg are taller than people in Moscow, probably. And I want to test it. Probably I have this theory, and I want to test this theory empirically. So how would we answer this question? What is our research design? Can you suggest one? Can you suggest a research design for this? If I want to answer this research question,
So we measure
what should we do?
several people, like 10 people in St. Petersburg and 10 people in Moscow, several like random people. So that is my first
Yeah,
suggestion.
we can consider two samples. We can consider sample, for example, sample SPB, and this sample contains heights of randomly selected people from St. Petersburg. So, for example, we have some values here. Something like this. And we have a sample from Moscow. for example, something like this. And I have different number of people in these samples. This is possible. I do not demand that the number of people here is the same as the number of people here. For example, due to some reasons, I was able to recruit only four people in Moscow. This is possible. And then I want to what is the next step? Um, what should I do now? I have these samples. How to answer my question using this sample, using these samples?
We should know the mean of the sample in each case.
Yeah, we can calculate sample mean. So sample mean of sample SPB in this case for this particular numeric values is 182, and for Moscow this is 170.2. And we see that in our samples, we see that sample mean that corresponds to St. Petersburg is larger than sample mean that corresponds to Moscow. So we see that the first one is larger than the second one. And again, the question is, can we conclude from this relation? Can we conclude that the answer to this question is positive?
No, probably. Well, just because we have different number of participants in each case, and also because maybe we just got lucky that we picked these people with this type of heights. So not really, I guess.
Actually, the fact that we have different number of people in both samples is not a problem for our research design. It is possible to have different number of different samples of different sizes. In this case, it is not a problem. We can calculate this sample means, sample averages, and it is possible to give a positive answer using even using samples of different sizes. But in fact, this this relation is not enough for us to make a conclusion that the answer is positive. Just because we understand that these numbers, these data are some kind of random things, the result of some random process, actually the process of recruiting of these people. And what we want to say, something not about these particular numbers, but we are interested in the populations that generated these numbers. We are interested, our outcome, our question is about people in St. Petersburg in general. So about the whole population of people in St. Petersburg and the whole population of people in Moscow. And what we have only some random samples from both populations. So just by comparing these numbers, we cannot decide that the answer to this question is positive. Just because it is possible that the result of this difference between this sample size and this between this sample mean and this sample mean can be attributed to so-called sample error of our sampling process. So randomness in our sampling process. And after that, we have to propose a statistical procedure that allows us to decide, do we have difference large enough for our sample size and for other properties of these samples, like standard deviation of these samples, that allows us to answer to this question positively. So again, the question is, what difference is large enough to make some claim that answer is true. Or in other terms, actually, as we discussed previously, we have several features of our experiment that affect this decision. One parameter is sample size. For example, if we have the same numbers, the same difference, but much larger sample sizes, this difference can be more convincing for us. And and it is possible that for large enough samples, even with this difference, we will be able to answer this question positively. So we are interested in this question. What the difference should be compared to our sample sizes and compared to actual numbers here. I mean the deviation of these numbers from the mean. That we will be able to answer this question positively. And the procedure is actually very similar to the one that we discussed when we discussed one sample t-test. Let me recall that in one sample t-test, we don't have two samples. We have just one sample and some predefined numeric value. And you compare your the sample mean with this predefined value and try to answer, is it true that you have a difference large enough to say that this sample was generated from population with different population mean. And here we do more or less the same. So let me state my null hypothesis and explain how my experiment works. So now I have two samples, and I believe that both samples are generated from its own population. So I have population in St. Petersburg. So this is St. Petersburg population. And I have some values here. And I use this population to generate my St. Petersburg sample. So this is, And then I have the same thing for Moscow. I have different different population here. And again, I use my sampling procedure to generate my Moscow sample. So this is Moscow population. So what I'm interested in are the averages of this population and this population. So I'm interested in the corresponding population mean. So I have, let me denote it by mu s per b. This is population mean in s per b. Population mean in St. Petersburg. And I have mu Moscow, which is population mean in Moscow. So basically, these population means are just average height of every persons who live in St. Petersburg, and this is the same for Moscow. These numbers are unknown to us. Actually, the only way to obtain them is to do complete census, but we don't have such resources. So instead of accessing to this population means, we use our sample means to approximate them, to estimate them. And then let us restate our research question in terms of null hypothesis and an alternative. What is our null hypothesis here? Null hypothesis is some statement about populations. How would you specify your null hypothesis in this research? Actually, null hypothesis is usually something that you want to reject. And more specifically, null hypothesis is usually some statement that something does not depend on something. So how would you specify null hypothesis here?
People
Any
in
ideas?
Moscow and St. Petersburg are of the same height?
Yeah. In fact, null hypothesis is null hypotheses are usually specified in terms like something is equal to something. So in this case, null hypothesis is that people, on average, people in Moscow are of the same height than people in St. Petersburg. So the average height of people in St. Petersburg is the same as average height of people in Moscow. So these two population means coincide. This is our null hypothesis. And what is alternative for this research question?
People in St. Petersburg higher than people in Moscow.
Yep. Exactly. Actually, an alternative is just a research question stated in terms of just assertion, not a question. So alternative is usually the thing that we want to prove. So this is correct. And now we construct a decision procedure. that takes into account our data and produces one of two possible answers, decisions. Either we reject null hypothesis in favor of alternative, or we do not reject null hypothesis. In fact, in this case, we more or less say nothing. Actually, again, this is the usual case for this kind of hypothesis testing. We can either say that we see some effect, that we see some difference, and this difference cannot be explained just by randomness, just by sampling error. We see that the difference is large enough to reject null hypothesis. The difference is so large that it is contradict to null hypothesis. We do not believe that this difference can hold if null hypothesis holds. And this is one possible case. And another possible case is that we do not reject null hypothesis. And in this case, we just say, okay, we don't know. It is possible that null hypothesis holds, but it is also possible that null hypothesis is violated. But the difference between these two means is too small to be detected by our experiment. Assume that this difference is just several millimeters. Then it is possible that we just, even if we have hundreds of people in both samples, it is possible that we cannot detect this difference in our population. It is just too small. And as our alternative just claims that there is some difference between these two population means, this difference can be arbitrarily small. And in any case, we can imagine situation when it exists, but it is just small enough to be detectable. So this is why when we say that we do not reject null hypothesis, we do not say that we accept it, and we do not say that we proved that null hypothesis holds. In this case, if we do not reject null hypothesis, we basically say nothing. So this is what we have. And now let me describe briefly how we would test this hypothesis, how we will construct this decision procedure. Are there any questions so far?
Maybe I have a small question.
Yeah.
Maybe it's not small because it's quite principle. You say that we say nothing when we reject null hypothesis.
When we do not reject null hypothesis, yes, basically, more or less, we say nothing. We say that we don't have enough data to see the difference. Probably it is a bit better. It is a bit better statement. So we don't have enough data, enough evidence to reject null hypothesis. So it means that probably it is possible to reject null hypothesis, but we just have to collect more data. But it is also possible that null hypothesis holds, and then no amount of data will allow us to reject it. So both cases are possible.
Yes. Then maybe my question is,
Mhm.
does our result really change if we just change our formulation of alternative hypothesis?
Yeah,
For
that's a good.
example, we
That's
could
mhm.
say that the high of the people in St. Petersburg is just different from people in Moscow.
Yeah, that's really a good question. We will discuss different kinds of alternative just a bit later, I believe, at this lecture. So the short answer is yes, we can obtain different result if we change an alternative, and we will discuss it just in a few minutes.
Thank you.
Mhm. So other questions? So to do this decision procedure, we actually want to do something very similar to what we did previously. So the idea is again as usual. The idea. First, we assume that null hypothesis holds. Then, under this assumption, so we assume that there is no difference between Moscow and St. Petersburg. Then, under this assumption, we we simulate how well we do the following. We try to reproduce our experiments. Actually, we do some kind of imaginary reproduction of our experiment. So we believe that null hypothesis holds. So these two populations have the same mean. Then we repeat selecting samples from this population and this sample and this population, and calculate sample mean here and here. And we do this a lot of times. So modal experiment reproduction. I mean the following. We assume that null hypothesis holds, and we try to understand how far can be the difference between our means if this null hypothesis holds, if the difference in population are the same. So we imagine that we create a new SPB sample and new Moscow sample. Find their means. Sample means. And difference between them. And repeat this process a lot of times. Like 10,000 times. So basically we will get a table like this, actually two tables, something like this. For example, iteration 1. we have Moscow sample. Okay, I begin with St. Petersburg sample. Sample 1. And we have, well, we have 5 numbers. And we have Moscow sample. Four numbers. And again, we find their mean of SPB, and we find mean of Moscow. And this is some particular number that can be calculated just by plugging these values, and we record this number. And then we do iteration 2. Again, we have our St. Petersburg sample. We will get different numbers here. And Moscow sample. And so on. So again, we have the difference. And again, we record this difference. So we repeat this simulation 10,000 times, just some large number of times. And then we get the distribution of these differences. Note that everything here is just complete our imagination. We try to imagine the world when null hypothesis holds, and we try to understand how results of our experiment can look like in this imaginary world. And the result of our experiment is just now, this is this difference between means. And then we have these differences between means, just virtual simulated differences between means. And we draw the distribution of these differences between means. How do you think how this distribution would look like if I draw the histogram of these differences between means? Differences between sample means. How these differences will be distributed? Can you say something about these numbers, provided that we believe in null hypothesis? So we believe that there is no any difference between Moscow and St. Petersburg in terms of the mean height. What can you say about the distribution of differences between sample means? What can you
Most
say about this
probably
distribution?
we still should expect normal distribution.
Well, it will be more or less okay. If your sample sizes are large enough, then under some yes, if your sample sizes are large enough, you can expect that this will be normal distribution. What else? What else can you say?
It's not really. It should be quite like steady. I don't know, because we do not expect much differences.
Okay, so where this normal distribution will be located? So what is the expected value of your distribution of differences? What is the point in the middle?
It should be to the left. Sorry, is my hypothesis.
We work now under assumption that null hypothesis holds. So what I'm asking about is the distribution of these differences, provided that null hypothesis holds. Now we don't think about our alternative and about our actual data. We think only about our this imaginary experiment, only about the theoretical distribution of these differences, provided that null hypothesis holds.
If it holds, it must be zero.
It must be zero, yeah. In fact, of course, it will not be exactly zero because we have some sample error, but it will be located near zero. So we have zero somewhere. And we have theoretical distribution that will look more or less like normal distribution. Not exactly normal, but quite close for large samples. And this is our theoretical distribution. This is so-called null distribution. So holds if null hypothesis holds.
But do we now speak about differences between differences?
We speak now about difference between two means. So at each iteration, we generate two samples. Sample from imaginary St. Petersburg and sample from imaginary Moscow. And then we calculate sample mean and find the difference between these sample means. And actually every recorded point here is just point on this horizontal axis. So there will be some distribution like this. Okay. Where do you see difference between differences?
I thought we spoke about differences between records, but now I got that. Now we speak about null hypothesis that there should be no differences between samples.
Yes. If we believe in null hypothesis, it means that of course it is possible that sample mean here is different from this sample mean. But the idea is that if we believe in null hypothesis, then we understand that the deviation to the positive side when mean in St. Petersburg is larger than mean in Moscow is equally probable to the opposite case when we have this difference, when mean in Moscow is larger than mean in St. Petersburg. So basically our picture should be, again, if null hypothesis holds, our picture should be just symmetric with respect to zero. Okay. So this curve shows us the distribution of these imaginary differences. This is how a world will work, provided that null hypothesis holds. What kind of results of our experiment can we obtain, provided that null hypothesis holds? And this is purely theoretical curve. Okay, in fact, to construct this curve accurately, we use some part of our data, but basically this is a pure theory. And now we have to plug our actually observed samples, not virtual samples that we generated here, but actually observed samples that we start with, these samples. How would we do it? What should we do now? Okay, actually, just before. Okay, yeah. What should we do now? We have some actually observed value. It is located, for example, somewhere here. Yeah, this is observed difference. And what should we do now? How our decision rule will work?
We should check if it's in the zone under the curve, which is more than 2 sigmas. I don't know how to say it, which is more, which is 5% of our
What 5%? How would you plug this 5% into this picture?
We should just understand where 5% of the sample lies, right?
Yeah. In fact, again, first of all, we just use our common sense. How our decision rule will work? It will work like this. If this observed difference is very large, then we will reject null hypothesis. If it is not so large, if it is somewhere here, we will not reject our null hypothesis. So our decision rule is the following. We have some value x critical again. So we choose some x critical, and then if x observed is larger than x critical, so x observed now is just observed difference.
Could you please repeat what observed difference is?
Observed difference is actually what we see in our data. So we started with these two samples, and these are observed data. I use the term observed just to distinguish between these samples that we actually obtained in our data and these samples that we created during our imaginary experiment. So these are some kind of theoretical simulated samples. And this data is our actual observed data. So for my observed data, I calculate this difference between means, between sample means. And now I compare this observed difference between sample means with these imaginary differences that I can obtain in my imaginary experiment when I believe in null hypothesis. I try to understand how much my observed difference that I actually observed in the data, how much does it contradict to null hypothesis? How unlikely to observe this data provided that null hypothesis holds. So to answer these questions, I put this observed difference on this picture. And then I say the following: if this observed difference is positive and large enough, it is somewhere here, for example, then I will reject null hypothesis because This is observed difference. Let us specify that this is SPB sample mean minus Moscow sample mean. So if this number, if this value is large, then this is an evidence in favor of my alternative. So if it is large enough, then I will reject null hypothesis. I will say that yes, people in Moscow, people in St. Petersburg are taller than people in Moscow.
What is X critical here?
X critical is some critical value. It is a threshold such that if my observed value is larger than this threshold, so let me put it somewhere here. If my observed difference is larger than this threshold, this X critical, then I will reject null hypothesis.
But how to find this?
Yeah, that's a good question. That's a good question, but this is next question. Now I just describe how my decision rule will work in principle. Then we will choose a particular X critical that will have a good properties. So.
So I'm sorry, I must have missed something, but why are we saying that observed difference is just 1 point? Why isn't it also a distribution?
No, because we have only one item of data. We don't know how it is distributed. What we actually have, we have basically, okay, we have two samples, but we are interested not actually in these samples. We are interested in the difference between their sample means. And using these samples, we can find just one numeric value, one difference. For this particular data, this difference, so this is observed difference equals to this difference 182 minus 172, and okay, it is very difficult to find this difference. I will use calculator to do it.
But I thought that we had to repeat the procedure many times, like we had many samples and we got many differences.
So look, we have this value, and this value is what we actually see in experiment. This is our observed value. Then we analyze our settings and analyze our decision procedure. To do this analysis, we forget for a second about our data, and we think how a world would look like if null hypothesis is true. We actually don't know that null hypothesis is true, and we actually usually want to reject null hypothesis. But now we imagine some imaginary world when we do these simulations, and in this way we construct this distribution. This null distribution. This is theoretical distribution obtained from our imaginary world. And in our data, we have only one observation. We cannot create more observations that we actually have. We have only one observed difference. So this is just a 1 point on this line.
Got it, thank you.
Okay. So why we do not reject null hypothesis if we get negative difference? Yeah, this is because our alternative that we are interested in is stated like this. So the question that we are interested in is the following: is it true that people in St. Petersburg are taller than people in Moscow? We are not under this alternative. We are not interested in answering the opposite question. It is possible to consider this alternative symmetric alternative as well, and we will do it just in a second. Yes, if we get negative difference, it is not an argument in favor of this alternative. So we are just not interested in it. Okay. Actually, sometimes we are interested in this kind of alternative. For example, if we test drug, we are interested. Is it true that this drug makes you feel better, make you recover faster? If it doesn't work, or if it makes situation worse, you don't need to distinguish between these two cases, just because they are both bad for you. In both of cases, you will not produce your drug. So sometimes we are interested in these kind of alternatives. Sometimes we are interested in symmetric alternatives and how to deal with them. We will discuss just in a minute. So more questions? Actually, this is really tough stuff because we have to, well, we have to take in our minds that we have some data and we have some imaginary world that we use to generate some imaginary data, and then to compare one with another. This is really complicated things. But this is actually how we. This is more or less common sense reasoning. You have some model of world, and if you see some data, some evidence, some new information, you compare this information with what is possible and what is not possible under your model of world. This is actually your everyday routine, basically. But this is just, in this case, we just formalize these things.
Sorry, may I ask a question?
Yes, sure.
So it's still not completely clear for me. How do we how do we know how this theoretical distribution can be? So for instance, imagine that the case when we have like three measurements, like 180, 170, 160, and so just like three measurements. And how do we know about like the rest? So imagine that, well, it's still possible that like the rest of the people in the city are like over 2 meters height, and how do we know that?
Yeah. That's a good question. In fact, to draw this theoretical distribution, you have to use your data in part. Actually, you use your data to estimate the variance of this theoretical distribution, and you believe that you have enough data to get more or less correct variance of the corresponding population variance. But of course, it is possible that you underestimate your variance. Actually, there are some mathematical tools that try to control for this possible underestimation. Just like in the example that you provided. But these tools work under some additional assumption. For example, if your actual distribution is normal, then there is a perfectly correct mathematical procedures that allow you to construct this distribution by looking at your data, even if you have a very small amount of data. The problem with this mathematical procedure, this is actually the core of t-test. This is actually what makes t-test different from just z-test that is based on normal distribution. Unfortunately, this procedure is justified only under assumption that your initial distribution is normal. Which is usually doesn't hold, and actually, if you have small amount of data, you cannot even test is it true or not. So basically, for reasonable amount of data, like thousands of points, you usually have good approximation of variance, and you usually can construct this theoretical distribution with enough precision. But if you have very small amount of data, yes, then things become shaky. So that's a good question.
Okay, thank you.
So let me complete this statement of our decision rule. We have to state how we choose this X critical. So if our decision rule is that if X observed is larger than X critical, so it is somewhere here, then we will reject null hypothesis. If it is somewhere here, we will not reject null hypothesis. So how to choose this X critical? Again, we want to make sure that probability to make a mistake and actually type 1 error is not too large. Again, as usual, we want to reject null hypothesis if null hypothesis holds with probability that is less than or equal to alpha, the significance level. And now we have a way to choose this X critical. We understand that if null hypothesis holds, then our observed value is distributed according to this law. And then if we want to make type 1 errors in, for example, 5% of cases, then we have to put X critical in such a position that, okay, if null hypothesis holds, then probability to reject null hypothesis is given by this area. Just by construction. So I just say that this area, so here we reject null hypothesis. So this area is probability to reject null hypothesis, provided that null hypothesis holds. So we want this probability to be less than or equal to alpha. In fact, in this case, it is better to just put to choose X critical in such a way that this area, this probability is equal to alpha. For example, 5%. This is how we choose this X critical. This is actually the same picture, more or less the same picture as you had in your second homework when we chose this X critical. But in that case, this X critical was a number of correct guessing. But now this X critical is just this difference between two sample means. But the idea is the same. We will reject null hypothesis if our X observed is here. If null hypothesis holds, then X observed is distributed with this law. And it means that if we want to reject null hypothesis with probability 5%, provided that null hypothesis holds, then this area should be equal to 5%. And this is the way to choose this X critical. Okay. Okay, let me ask a question. If I choose instead of 5%, if I choose alpha that is equal to 1%, what happens with X critical? So assume that I have a picture like this. I have this X critical, and I have alpha 5%. What happens if alpha equals to 1%? Where should I put X critical in this case?
To the right.
Yeah. Then X critical should be somewhere here. So this is 1%, and this is 5%. So in this case, X critical will be shifted to the right. In fact, what does it mean? It means that if you want to make type 1 errors less often, then you have to make, well, you have to increase your threshold. You have to become more, how to say it? You have to say that you see the effect more rarely. This is the way how you can decrease type 1 error. Okay.
But shouldn't be alpha, it should be always 5% or?
Well, basically it depends on the field. In linguistics so far, as in social sciences, people use significance level of 5%. It is possible that during the future decade, this will be changed. And for example, people will switch to 1% because probably this 5% is too large probability of making an error. But currently, yes, it is 5%. But it is possible that in some problem you are asked to use different significance level.
Yeah, you can prove that in other fields like medicine, psychology, cognitive neuroscience, it's more or less the same, but there are many articles like that try to decrease this level to 0.01, but well, it did not succeeded, and so there are many discussions about that, like article, for example, Justify Your Alpha, where you need, where the point of authors, like you need to justify your alpha in every study that you do and explain why you choose this one, but it was not like accepted in broader community, but it's, well, the topic of the discussion in many fields actually.
Yeah, thank you.
So can you
mhm.
specify one more time how to find X critical?
Okay, X critical, actually, basically you don't have to do it by yourself, but theoretically this X critical is found from the next considerations. We want to make type 1 error with probability less than or equal to 5%. What is type 1 error? Type 1 error is when you reject null hypothesis in case when null hypothesis holds.
Mhm.
So if null hypothesis holds, then your difference is distributed according to this curve. Just because we constructed this curve with this condition. This curve is exactly the curve of distribution of this difference provided that null hypothesis holds.
Okay, so to find x critical, we should find probability to reject null hypothesis. Yes.
So we understand that this probability to reject null hypothesis, provided that null hypothesis holds, depends on x critical. It depends like this. This is the probability to be here, provided that you generate your difference according to this curve. So this is basically just this area. This area is proportional to the probability to obtain value that is larger than this x critical from this distribution. And then you just choose this x critical in such a way that this area equal to your 5%, because you cannot make it larger and you don't need to make it smaller. So basically, if you have this curve, you just do the following thing. You just start from here, and then you decrease your x critical, and you decrease it until this area would become 5%. When you have this, you stop and you say that this is your final x critical. Okay. Yeah.
But how to do it technically?
Well, you don't have to. Just well, basically, if you have this curve, and you can find these areas, then you can do it. Technically with some programming or some calculations. Usually some programming. But now just you don't have to. In fact, if you know this distribution, and you have well, just you don't have to. Okay.
Okay, and if we, for example, get probability to reject null hypothesis provided that null hypothesis holds, and it is like, for example, 3%.
So if you choose this x critical, and you see that this area is 3%.
Yes.
Well, it means that you can decrease your x critical and make your test more sensitive. In fact, the larger x critical, the less sensitive is your test. So the larger the larger x critical, it is less likely for you to give a positive result, to say that you reject null hypothesis. And so there is a trade-off. You cannot make this x critical too large, because in this case you will just never reject any null hypothesis. You will just say that, sorry, I don't see an effect. Sorry, I don't see an effect. I don't have enough data to show you that effect exists. And if you put this x critical too small, then you have another problem, that you will do type 1 errors, that you will say that, okay, I see an effect, but there is no such effect. So there is a trade-off between your like ability to make some claims and your probability to make type 1 error. And so you put your X critical in such a way that this probability to make type 1 error is exactly 5%.
Mhm.
If
I'm
you put
just
it, if you put it here, your test will be also correct. I mean that probability to make type 1 error will be again less than 5%, but it will be not so sensitive as the test with this X critical.
okay. I'm just now thinking how to find this probability, and like in the tasks with magician, I knew how to do it, but in this task,
Yeah, because in the task with magician we have so-called discrete distribution, and all probabilities are found by summation. In this case, you have to integrate this function. This is called a probability density function, and to find these areas which represent probabilities, you have to do integration. But I don't want to scare everybody with large integrals, so I just say it in geometrical terms. But basically, if you can integrate this curve, then you can find all the probabilities that you're interested in.
okay.
Okay, so yeah, I have a final words actually about all different alternatives. Let us discuss what happens if our alternative. So again, our null hypothesis A is that people in St. Petersburg are of the same height as people in Moscow. And first of all, let us discuss an opposite alternative. What changes if I consider this alternative? First of all, how our decision rule will work in this case. Again, I have to fix some X critical. And what should I do next? How our decision rule will work? So X is sample mean SPB minus sample mean Moscow. So if my alternative is this, how would you state your decision rule? When will you reject null hypothesis? I put X critical to the left of 0, okay. And how the decision rule works? So if my alternative is like this, then an evidence in favor of this alternative is not very large X observed. It's not something that is here. But on the other hand, it is quite opposite. It is X observed that is negative enough. So somewhere here. So the decision rule is if X observed is less than X critical, then reject null hypothesis. And now to find how this X critical is located, okay, our rejection region now is this region. So the probability to make a type 1 error is this area. And
excuse
now,
me, excuse me, but do you
yeah, it
draw
doesn't show.
something new?
I see.
Yes,
I see.
it doesn't show.
Yeah. So now now we will reject null hypothesis is if our x observed is somewhere here, negative enough, and the corresponding probability to make type 1 error is this probability. And again, I put x critical in such a way that this probability is 5%. So everything is symmetric. Okay. So it was an easy case. Now a more difficult case. What if null hypothesis as previously? But now alternative is that they are just differ, and we don't know in advance which case is more interesting for us. How would you state your decision rule now?
So now there are two x criticals, yes, like to the left and to the right.
Yeah, in fact, it is easier to work with just one value. We have a symmetrical picture, so let us put x critical here and negative x critical here. And we will reject if the difference is too positive or too negative. So it is far enough from 0. So reject null hypothesis if x observed is larger than x critical, or x observed is smaller than minus x critical. And now that's an interesting question. How should you choose x critical now?
So 5% rule would not work here, yes? It wouldn't like.
Again,
as we did it previously, yes.
Again, you have to choose such x critical that probability to make type 1 error equals to 5%. But what is the probability to make type 1 error now on this picture? If you reject here and here.
10%.
No, you keep your so you keep your alpha, your significance level to be 5%, and you choose your x critical in such a way that it is 5%. So, but how to express your probability to make the one error in this picture now? For example, on this picture, this probability was expressed by this area. What about this picture?
So we should find 2.5% of data on each side and
yeah,
put x critical there.
Yeah, exactly. In fact, now the probability to make type 1 error, basically you have more or less twice as much ways to make type 1 error. Previously, you had only this way to make type 1 error. And now you have two ways to make type 1 error. You can be either here or here. And you want, so the probability to make type 1 error is just sum of these probabilities, sum of this area and this area. And it means that if you want for the whole sum to be equal to 5%, you put here 2.5% and here 2.5%. So under
Excuse me,
this,
and
yes.
could we imagine cases where there are like 5 x criticals or 10 x criticals, and therefore we should divide this 5% to 5 or 10, or it is just impossible, like to have many x criticals?
Well, in a sense, but basically you have it is correct that you have to take into account the structure of this set when you reject your null hypothesis. And sometimes, in fact, you have to divide your significance level by some numeric values. This is, for example, this happens when you do multiple comparisons. And this is so-called Bonferroni correction, when you divide your significance level by number of comparisons. And we will discuss it later when we will discuss this multiple comparisons problem and another test. But not on this picture. On this picture, you usually have just either this kind of picture or this kind. So if you compare two cases, when you have this alternative, or when you have some one-sided alternative, where x critical will be larger. So for this picture, or for this picture, where x critical is larger. So you see that here you put this x critical in such a way that this area is 2.5%. And previously we put x critical such that the corresponding area is 5%. So previously it was smaller. Here it is larger. So when we consider this alternative, you have to provide larger x criticals. Okay. Because you have more ways to make a mistake. And just a last word that I want to say, that instead of comparing your x observed with x critical, you usually consider this p-value. P-value, again, let me repeat this definition. In this case, what is p-value? For example, if you have one-sided alternative, then you have some observed value, and the p-value is this area. This is your p-value. So p-value is probability to obtain data that we obtained, that we actually obtained, or more extreme, provided that null hypothesis holds. So what more extreme means depends on the alternative. If alternative is this one, then more extreme means larger. For opposite alternative, more extreme will mean smaller. For symmetric alternative, it is a good question what happens in symmetric alternative. So And your decision rule is the following. If p-value is less than alpha, then you reject null hypothesis. Indeed. Again, you have to compare this picture with the picture with X critical. And if you know that that this area is alpha, then you see that if X observed is to the left from X critical, then p-value is larger than alpha. And you do not reject null hypothesis. If X observed is somewhere here to the right from X critical, then your p-value, which is this probability, it is less than the um, critical level. Sorry, it is less than the significance level. It is less than alpha. So you see that this decision rule in terms of p-value equivalent to the decision rule in terms of X critical. But it is easier to use it, and this is actually what will you do. So are there any questions so far?
Yes, I have a question. How should we choose between alternative hypotheses? I mean, in some cases,
Yeah, it depends. It depends on your research question. It depends on what you consider as a question of interest. So
yes, I understand when there is a motivation. It's quite clear, but isn't it more fair in each case to expect two possible outcomes?
well, if you don't have any, if you don't have any if you cannot state in advance before looking at the data which outcome is more interesting for you, and actually, if you can say that one outcome is interesting and another is not interesting, then you have to choose a symmetric alternative. This is correct. So if it is not obvious, then probably you need a symmetric alternative.
Okay, but it's not so that it's more, yes, it's more fair to always choose symmetrical alternatives.
Well, it actually depends on what will you do in so for example, I believe that I don't know exactly, but I believe that in drug testing people can use non-symmetric alternative because it is not interesting for your just absence of effect or negative effect are the same for you as and what is really interesting is positive effect. So sometimes you can imagine situations when you can state symmetry. You can state a symmetric alternative. Just your theory suggests that this inequality should hold, and you want to prove your theory. Then you can use, for example, if your theory suggests this, and you want to prove it, then you can use this alternative. But in this case, you cannot at the same time, if you have negative result, if you have a result like this one, you cannot at the same time propose a new theory that in fact it works in the opposite direction. You just say that you can say nothing. So this is how it works.
Okay, thank you.
Other questions? Okay. I want to I want you to think about and begin seminar with the following question: how to define p-value in case of symmetric alternative. And then you will use our function that allows you to find these p-values, and then you will interpret the corresponding results. Okay, then that's all with the lecture for today. So I hope that we will begin exercises, I think, in 10 minutes. Yes.
Thank you.
Bye.
So hi everyone, we'll start in 1625. Okay, hi everyone. Do you hear me?
Yes.
Yeah, cool. Okay. So today we are going to continue doing such things about tidyverse. So I want to cover a bit what we did previous time. So we learned some very basic thing about tidyverse that is very deeply integrated in the whole tidyverse, well, let's say pipeline, because it's a pipe. So basically it is a very important operator that do this thing. So if you calculate, I can show on previous code that we wrote previous time.
Excuse me,
yep.
I think we have some like strange error. So you demonstrating the demonstration of your screen. So so for example,
Yes,
okay.
chat.
It's a bit hard to see what's in your R.
Okay.
Yeah.
Okay. Let's do it this way.
Now it's cool.
Yeah, it seems like I have glitches of my camera. Okay, that's kind of strange, but sorry. Okay. No, I have glitches with my camera. I don't know why. Okay. Can you hear me this way? Do you hear me?
Yes.
Yes? Okay. Okay, so let's return to our studio. So we learned about this pipe and what is important, how it works, that takes what you have in the left part of the from left side of the pipe. For example, this is a vector from 2 to 8, and takes it as a first, or from 1 to 22, and takes it as a first argument, as a first parameter to the function or that is on the right side from the pipe. And because in general what we do with our data is something like we just apply some functions over some data set usually, we can use this pipes to organize our code, and it looks nice. It's very readable, and it's pretty easy both to both read and write. So and in some cases, for example, if you want to control where you put the result of the operation on the left, you can use this dot as a placeholder. So, for example, if you want to calculate logarithm with logarithm of 8 with different bases, you just use like 8 and then base equal to dot, means that you will take into a dot as a parameter result of this operation. It is very important thing, this pipe in tidyverse, because basically base dplyr operation. Dplyr is the most important package in tidyverse. they're all built on the idea that you do some operations on some data frame or table as a modified data frame, and like in future we will use data frame and table interchangeably, so you can just it works for both. So the idea is that you apply some functions to modify some data frame. It is not internally modified. Just apply some you apply some function, and you get you get in return some modified version of your data frame or table. So let's try it on the example with heroes, and we'll learn some basic verbs, some basic functions of dplyr first. Okay, I will send you the link in chat, and now you can use this function to just download and import here's the data that we worked previously. Okay, so the first thing that you want to do usually with data, you want to select somehow several columns or rows, but we will start with columns. So you know about some basic data frame subsetting. We used like heroes, and then square brackets, and then we selected rows by specifying something before the comma, and then by specifying by something after the comma, we selected columns. So when we work in tidyverse, forget about it. Sorry. We do it another way here. So if you want to select columns, or you want to do whatever you want, you need to specify a function for that. So if you want to select columns, you use the function select. Select. You can select columns by index numbers. So I want to take the first column and the fifth column. Okay, I get the result. Nice. Actually, in general, it's a bad idea to use selection by numbers. It doesn't matter whether you work in basic data frames, in data table, in tidyverse, or even in Python's pandas. It is not good idea when you work with the data to select them by indexes. Like, I remember that my column is the first column or is the third column. Do not rely on that, because usually in the data, when you analyze the data, it doesn't matter so much what is the order of columns. You usually can sort order just because it's easier to work with like ID column in the first and some other columns in the right part of your data frame. So it doesn't matter really much. So it means it is not really a good idea to rely on the order of columns. So it's better to select them by name. So for example, you can select if you want to check names, or you can just open it. You can see race, height, publisher, weight, gender, and so on. So I want to select name. So here you specify it like it would be a variable because you don't use quotation marks. You just use it like it would be a variable in environment. But actually, it's something like a variable in this table environment. So consider like heroes is actually something like a small environment that has these columns as separate variables. And you select them without any quotation marks. So for example, you want to take race, publisher. Yeah. Also, you can you can find out that there are some ticks there, back ticks for eye color, for hair color, for skin color. Why does it happen? Do you have any ideas? Why do we have these ticks here and we don't have ticks here, for example?
Because it's the variable that is in this column. It's categorical, maybe, I don't know. I mean, the list of values that is possible in this column is restricted.
Yeah, exactly. So actually, it creates us a problem that if you want to select, for example, heroes by this $sign, eye color, you can see this ticks are created automatically, but without it, it just cannot be interpreted by R because there is this white space and it is the end of the variable and then another some color thing. You know, you can just find out that, yeah, it's simple there. So yeah, or more generally, this eye color with white space is not a valid variable name. So variable names in R, they do not contain, they does not contain white spaces. But it doesn't mean that variables with invalid names cannot exist. They can exist, but we are somewhat restricted when we work with them. So either you convert it, for example, you convert white spaces to dot, what is done by basic read-c3 function by default, or you use these backsticks to when you want to do something with this column. So yeah, and in this case, you do exactly the same. Eye color, eye color without you, right? Yeah, and without this. Yeah. So now after we apply function select, we have in return another table with columns that we selected. What is important, we didn't change anything in the heroes table. So it still contains all columns that we had when we imported this data frame. So when you want to save your result of save result of operations in dplyr, when you work with dplyr, you need to assign that to some variable, for example, heroes with less columns. So now you can see that was saved as another variable with less columns. Actually, selecting columns is a bit more complicated than you might think. Actually, it's something like a mini language for selecting columns in tidyverse called tidy selection. So there are actually much more rules that you can use, and they're really nice. They're really nitty, and it's pretty easy to use it, and you don't need to learn this language a lot because it's basically just few operations that you can use inside select function and inside some other functions that use tidy selection, because actually there are much more functions than just select functions that where you can use this tidy selection. So another thing from this tidy selection mini language, it's called mini language, is that you can use this colon operator to select several columns. So I think it's pretty obvious what this colon operator uses. Do you have any guesses?
Well, it selects all the columns in between name and publisher.
Yeah, exactly. So it's how it works in pandas, as far as I remember. It's how it works for just simple atomic numeric vectors. So yeah, you just take from all columns from name to publisher. Moreover, you can combine several selections. Like you can take, let's say, from name to race, and from publisher, and from height to publisher. Okay. Another thing from this tidy selection language is that you can choose what columns you don't want to use. So, for example, you have here a column called x1. It's artificial. It's an artificial column that was created because there were some numbers 1, 2, 3, 4, 5, something like an ID in original CSV file, and you want to delete it, for example. So you use exclamation mark or just minus. It works the same way. So both ways will work. And in this case, you just do not select columns that you specified. The same works if you want to select, do not take several columns. So you just use like this. You use this column and an exclamation mark to select columns that you don't want to use in your data frame. Okay, and also there are some other nice operators there. So for example, logical or and, like these operators, they also work inside tidy selection. But also there are some helper functions, so tidy selection helpers that you can use to select columns that you want. For example, you want to select everything from some column, for example, from race to the last column. And for this case, you have a function last call. This function will work only inside this tidy selection environment, only in this tidy selection framework. Another important function is select everything. In this case, it will just return the same table. But in the future, when you need to select some columns in different functions, and you want to say like, I want to take all columns. Actually, I don't want to select some of them. I want to take all. You just press everything, and it will return every column and apply some function over all columns. And what is important about this everything, it somewhat counterintuitively, but actually it's pretty nice behavior. So it will not repeat columns that you specified somewhere else inside the select function. So for example, if you want to take as a first column name, as a second column publisher, you can press everything, meaning that you want to take all other columns too and put them after name of publisher. So something like a relocation of columns in this way. But actually, for movement of columns, it's easier to use a relocate function, but we will cover it a bit later. Another interesting thing about selecting columns that you can use selecting columns by matching some pattern inside. And usually it is used for several reasons. So usually you have either some number of columns with the same suffix, or for example several columns with the same prefix. For example, you give some test to your participants, and it returns you some different traits, some psychological traits, and they all have the same suffix to make operations on them easier. And in this case, assume that you want to take all columns about color, like eye color, hair color, skin color. In this case, you want to just use and with and color inside, and you will receive all columns that has color in the end of their column name.
But I'm sorry, but you started to talk how to select words with a certain suffix, but you didn't show it.
It is not about selecting words with a specific suffix. It's about selecting columns that have names with specific suffix. So it's this ends with works only in the context of selecting variables, selecting columns in a table. So it has very specific purpose. So if you want to do some more complicated operations on text, I recommend you. Oh, actually, it's a long story, but I can just tell you about packages called string I package that has many functions to work with text, and string R package that is actually part of core tidyverse, and actually it's mostly a wrapper over string I package that has simpler, and stringer has just simpler interface to use than the original string I package that is actually more powerful than string R. And of course, yeah, maybe we'll cover it if you need it, because actually in R you can do everything with the text that you want to do, and it's pretty easy and straightforward. So you can use, of course, even in base R you can use regular expressions. There are many packages for natural language processing, and yeah, so, but in this case, I talk about just selecting columns. Yeah, the same you can find a function that do more or less the same thing, but for selecting columns by prefix in their name, called starts with what? Let's say H. Yeah, we have columns, color and height, for example. Actually, it's not all, because yeah, sorry. Yeah, actually, you can just find some columns that just have some specific pattern, and it doesn't matter for you where this pattern, where do you have this pattern. This word contains, for example, 8, and you get 8 and 8. And there is even a function that you can where you can use regular expression to find specific column names. It can be useful if you have very wide data frame, and it's pretty hard to analyze it. And if you have, for example, for some reason, like several hundreds of columns, and they have some pretty names, it can be useful to you to apply regular expressions to parse this big data frame. And the final thing that you need to know about selecting columns is the function where. It's something like apply or map functions, but for selection. Oh, sorry, select where. It's something like apply functions or map functions, but for selecting columns. So how does it work? Inside this where you give a function, not like a function name, not the result of the function, but function as an object. So function is a first order object in R, and here you can find the use of it. And this function is applied to every column. And if after application to the column the result is true, you select this column. Sounds a bit complicated, but the usage is pretty straightforward, and it's very helpful. For example, you want to take only numeric columns. How do you use it? You put inside where function is numeric. Is numeric is just a function that check either is a vector numeric or not. So for example, you give it 1, 1 to 3, it's numeric, it's true. If you give it like f, it's false. If you give it like true logical value, it's false. So is numeric returns true only when you give inside function numeric vector. And here it's applied like this. So this function is numeric, is applied to every column in the data frame. If it's true, so it is a numeric, you have this column. This column is returned in the final, in the result, in the output. Or the same character is character. Actually, from here you can find actually that it's really mind-blowing, and you can do really complicated operations on selecting columns. So you can select columns by application of some pre-specified function, and you can use it inside it, or you can use anonymous function here. For example, function that is numeric. No, I think, yeah. If is
Okay, if it's numeric, no, I think. Where, okay, let's say, let's do something different. Where we apply function and char that will return number of symbols. Actually, it's applied to character vectors. So for every value, it returns number of symbols. And let's say you want to take only columns where only columns where number of maximum number of characters inside one string is not more than 10. Oh, I forgot something. Constant. Yeah. Max and char. Let's see. And char. Max. Okay, I have. It returns true. That's strange. Or false. Okay. Yeah, I forgot. It returned an A, and because of an A, it returned error. So in this case, return only columns that are not white. Just example from ahead now. It was a bit of improvisation, sorry. But actually, this gives you a lot of power. For example, you can get all columns that without an A, for example. And you say where function x is an A, x, and let's say, so in this case, you say, if you have any NA, return, if there is an NA, it will return true. Then if you have at least one NA, it will return true. And we want to invert, so we use exclamation mark. So it means that if there is at least one NA in a column, it will return false and it will be not returned. In this case, we can return only columns that has no NAs inside. So, you know, like you can think like, okay, but selection columns is pretty simple. Why do you need such complexity? But you can have it, you can do it. And in some cases, when you have very wide data frame, it's really nice to use it like that. It gives you a lot of flexibility. And it's really nice to use. We did actually quite complicated operation, just one code. Okay.
So can I ask?
Yep.
The first one, this structure with function x and then function, should we always use it like that, or can we just put max and char x is smaller or equal to 10, or should we write it as a function?
Well, yeah, good question, because For example, yeah, let's see this example. Yeah, you need to have you need to have a function as an argument to that. So, for example, assume you do it like that. So you do it like that, like yeah, for example, like that. The problem is that this is not a function. It is considered as some kind of data that is a result of application to some x that we don't have, right? So in this case, it's interpreted like, okay, apply function max to result of n char applied to x. So if you delete it like from here, like it's not a function, but if you have some x, for example, like this, it will be an operation as it work. So what is different here that it's here you need to have a function inside, and it's pretty complicated idea that you don't in this case use not result of some operation, some application, not result of application of some function to something that is already some data to function. You apply a function to function, so you have an argument that is considered to be a function, not a result of function application. You can't find function max because you apply. I think you have this here, not this. It is not. I do not want to assign 10 to that. I compare that to 10. Right, so I think that your error is caused by that. I just compare this to 10. I not assign 10 to to some variable here. Okay, and so what can you do here? You can do it like that. You can, if you have just a pre-specified functions, or for example, a built-in function or whatever, you can use the name of this function. In case this is this column will be the first argument to the function, but in case it is not like that, for example, when we applied like isNumeric, for example, right? isNumeric. So in this case, it is a built-in function isNumeric that as the first argument has some vector and returns true or false, depends on whether the vector is numeric or not numeric. And yeah, in this case, we can just write the name of the function. In case we don't have such function, we can just create it. For example, we can like use this code to create a function x over s, and let's call it is short. Or is value short. Yeah. So this function will return true if all values. Oh no. I will call it values short. So it will return true only in the case when all values inside the vector are short. So for example, let's say something like that, and it will return sorry. It will return false. If we shorten this one, it will return true. And then when we create this function, we can do it like that. We can use it inside where when we select variables. It's important again to understand. So I know you can think like, okay, just about selecting columns, but it's not only about selecting columns. It's not only because tidy selection is used everywhere in tidyverse now, in many functions. And also this logic, this functional logic is very important when you work in R. So basically how it works is very similar to supply functions. When you just apply some function to some data frame or list and return result of application of every function to every item in the function. So the logic in the syntax is very similar. So here you can also use you can put parameters after the name of the function that you want to use inside this function, and so on. So the logic is very similar to pur and to supply-lapply functions. Okay. So also some other nice functions that use tidy selections. Tidy selection syntax. It's first the function rename. Just renames variable. So you select like id equal to x1. So it means that you want to rename variable x1 to id. That's basically all. So we had x1 here, now we have id. Again, it is not something that change original heroes data frame. In the original hero data frame, you still have x1, but it returns modified table with new comment. And another nice function is a function relocate. Actually, you can just relocate by using select function. You just need to select every function, every column that you want, and do not forget about all other functions too. But relocate just gives you some more gives you some easier interface for that. So you just say relocate publisher. It means that it will be put in the beginning of the data frame, or you can divide it by parameter after. So you want to say I want to have publisher right after the column name. Okay, you have a parameter before and after that will do it. Again, if you put instead of after before, it will be like column before. It will be like column publisher before the column. Yeah, I think it's problem with connection, but okay, let's try to do something and
let's do it like that. And of course, you can use all this power of tidy selection for use all the power of tidy selection to select your columns or relocate your columns or name columns. So all the things, they also work in relocate. For example, you want to put publisher first, then all numeric columns, and all the selected columns, publisher and numeric columns you want to put after column name. And that's it. So it's pretty complicated operation about reordering columns, but it's done pretty much easily using this tidy selection syntax. So now please do some tasks about selecting about using tidy selection. Starts from here. Yeah, starts from here. And before until this. No. Until this, until row selection, deploy slice. Yeah, I have some problem in this online book. Okay. So please do these tasks, and if you have any problems, just ask me about that. So there are some tasks about how to arrange columns in the order, to select specific columns in the specific order. And also for for these tasks you need another table, but you can find the link here. I don't need to copy it, I think. It's table powers. It's from the same, it's relational data set to heroes data set. It contains hero names, but some of superheroes from heroes data set they do not appear there, and vice versa. So actually, it's very wide data frame where you have hero names in the first column, and all other columns is whether they have some superpower. No, it's different rows. And in this case, yeah, exactly. So you start from dplyr select functions. Yeah, so everything from here, everything from the point where you need to import data. Yeah, something like 5-10 minutes, but it is always, it depends actually on your success. So if you did everything, just press plus button. For example, if there are too many questions, I will give you more time. In the case too many people do it very fast, we'll move a little bit faster. So this part is a bit flexible. Do you have any questions for now?
How to say you are done?
Sorry?
How to indicate that you are done?
With plus, you just send plus if you did everything. Okay, nice. Okay, so I will give like the last minute to finish the task, and then we'll continue to selecting rows. Okay, so do you have any questions? Do you have any problems? Because like there were not so many tasks, so I think it should be pretty straightforward to just give you some experience to get used to basic tidyverse operations. But if you have any questions, don't hesitate to ask me about it. Okay.
Yeah, so sorry.
Sorry.
Yes. Yes.
I have a problem with selecting first 4 columns. So do we should we do it like by hand, by like typing the titles, like we did it like name, eye color, etc., or there is some shortcut that we discussed?
So which one?
Yeah, I mean like the very first task. Should we like type select and then type the titles of the columns, or
you can select it just by numbers, just by vector 1, 2, 3, 4, 5, 1, 2, 3, 4.
Okay.
Yeah.
Yeah.
It is not recommended way of using that because I explained it before. Why? Because usually it doesn't matter what order of columns you have in your data usually. So if you change order of columns, usually doesn't matter a lot. And if it does, it's usually like a big red flag about your data. But for some cases, for example, we just want to like to scroll through the first columns or some columns in the middle and so on. It can be useful. Okay, so let's continue. So we talked about how to select columns in data frame, and now we will talk about how to select rows in data frame. The very basic and simple function is the function slice. It just takes rows by number. So you just select by number. For example, you want to select the first 6 rows, like function head. So here I use the vector 1, 2, 3, 4, 5, 6, and select these rows. So like you want to select the second, the fifth, and the 10th row, you use a specific vector. As simple as that. So pretty simple, pretty straightforward. The next thing is selecting columns by some condition. And in this case, you use function filter. So just try to remember, slice will take rows just by number, by index. So the most simple way to extract rows. Filter will take rows by some condition. For example, you want to explore only DC comics. DC comics like Batman and Superman. Yeah. You can even fly here using ent and find some Batman or something like that. And what is important here that it's pretty similar to the idea when you select some rows using base R, but when you use base R, you use like zeros, dollar, publisher, and so on. Here's the same as for tidy selection, but with a bit different mechanism. It's called data masking. You select rows by some vector manipulations on columns that again are considered as like variables inside this heroes environment. And it means that you don't need to specify heroes dollar. It wouldn't even work, I think. No, it worked. It works. Yeah, it works. Yeah, right. But you don't need it. You just you can use just publisher that is considered as a variable inside heroes environment. And let's select it. You can, of course, combine some different conditions. For example, I will use a function from string R package to find some pattern in name that will be like bat. I want to find Batman. And I found it. And I also found Batgirl, Batgirl 3, Batgirl 4, Batgirl 5, Batgirl 6, Batman, Batman 2, Batwoman 5, and Batgirl and Batwoman are different superheroes. And also Man-Bat, somewhat, I don't know what is it, and maybe it's for better actually. Another way to select rows is a bit like new one, but I really found this way pretty useful, and I use it really a lot. I use it really often. Is a family of slice functions. So this basic slice function has also some other options, some other variants, and they're really nice. So for example, slice max will return some number that you specify of values by maximum value from a specific column. For example, you want to select columns, you want to select row with a maximum value for weight, and you just do that. Sasquatch weight 900. You can specify number of maximum values, and also be careful because when you have ties, so for example, in case somebody will have exactly the same like 900 as a weight, it will return both options, but you can specify it in argument slice max slice max. With ties. Yeah, with ties. So if you put with ties, for example, like 10 maybe. Yeah, you can see that we have not 10 but 11 because a bomb and abomination, or I don't know who is it, they have the same weight. And that's why we received not 10 but 11 superheroes, 11 rows. So in this case, if you want to do like return me at least one of them, and it doesn't matter for me which one, so you just say with types equal to false. The same way will work for slice mean. Very nice function, and I think it's more or less straightforward what it does. The same, but for it will take not top, like the least heavy superheroes here. And another thing that is pretty nice is slice sample. It will just take random sample from your data without replacement by default, but you can specify that you want to do it by with replacement. Replace equal to true, so they can be repeated in this case. Another nice way to use this function is to put prop equal to 1. Okay. I like how explicit tidyverse is. So must supply exactly one of n and prop arguments. So just say prop 1, and it will just randomize order of these rows. Pretty nice way to do that. Or you can select some percentages. If you say like 0.1, you will take 10% of superheroes. For example, you want to divide your sample for test and training, and you can use this function, for example. Another nice function that can be used for selecting NAs, for selecting rows, or actually to work with NA data, is a function from tidyr package, drop NA. Actually, it does not matter where the function comes from, especially when it comes to dplyr and tidyr, because it's very hard to find the border between these two packages. They both are for data manipulation, but tidyr is more focused on data cleaning, and dplyr is more focused on manipulation of data. So it's a bit tricky where manipulation ends and when tidification starts. It's usually somewhat combined, but in this case, well, it can be like considered like when you do something with an ace, it's something like a tidification of data, right? Okay, so the very simple way to use it is just use functions as like drop an A without any arguments. And it will do like very straightforward thing. It will delete all rows that contain at least one NA. Something, yep, sorry. Allo. If you wanted to say something, I cannot hear you, sorry. You can write. And also you can use you can use tidy selection. So you can use tidy selection here to select variables that you want to use to drop NA by these columns. So what does it mean? For example, you want to let's say you want to delete all rows that have NA in a column weight, but it doesn't matter for you if you have NA in other columns because you are focused on analysis of weights of superheroes, and in this case you don't want to, you're not interested at all in rows that do not contain this column, but you are interested in like in other columns, maybe even if they contain NA. So you just say wait, and that's all, and you receive that. Also, yeah, as I said, you can use tidy selection there. So it will be like, let's say contains 8 pom pom, and you selected in this part both weight and height, and you drop all columns that all rows where you have an A in either height or weight. You can see in these columns you don't have an A, in these columns you don't have an A. Or the same like ends with color. Again, now you don't have superheroes if they have an A in one of these color columns. Okay, let's see about tasks. What do we have about tasks? Okay, yeah, please do the next tasks about row selections, row selection, about slice and filter, until you have a range. Yeah, within a selecting function. Could you please, Alexander, could you please, yeah, okay. How do you use within selecting function? Interesting, because, sorry. Maybe you just selected contains this and started and press Command Enter, and you so that you use this function outside of tidy selection framework. Okay, if you finish, send a plus. If you have any questions, please ask.
Whew.
So in the first, we should use slice max function.
Sorry?
So in the first, about weight more than 500 kilograms, we should use slice max function or just slice
Try to
function.
remember this way, like if you have selecting by conditions, you use filter function. If you select just by number, you select with a slice function. And yeah, in this case, obviously there is a condition, weight is more than 500, so you need a filter. Like you filter by some condition.
Okay.
And when you slice, you just take a slice of your data frame based on some numbers. And it's usually how it's used. So slice is usually used when you just want to take some rows to explore what you have in rows in these rows, or take like the first row, or like random rows, or the last rows. And when you use filter, you just like you filter your data frame. And please press plus if you finish it. I mean, it's just 3 tasks, you know, just 3 of them. I think it should be pretty straightforward. I think it's this part is more simple than like when you need to create functions or like for functional programming. Because tidyverse was created to be simple, readable. You just need to learn some basic words, how to combine them, and which basic operations you actually have when you do some analysis. And knowing this basic verbs, you can do almost every analysis that you want in a pretty easy and straightforward way. So what is the advantage of tidyverse compared to basic R processing or data table data processing? That you uses words that do specific things. You do not think about like where you need to put square brackets and so on. You can just use in terms of operations. So if you need to
filter only females and then group them by university and then calculate mean by these groups. You just do it this way, and it's simple as that. No, actually, yeah, you need to use slice and filter functions. But what is important that, yeah, of course, you need to somehow, it is not like you just copy paste or change something and get the result. Every task here is, you need to think about it somehow. You need to combine instruments. I just give you tools and you need to think about how to apply these tools. For tidyverse operations, I think it's that most tasks are not that hard, and some way in some examples, just you need to like change less to more and something like that. But it means that in general you need to like to think about it creatively. It is not like you can find some algorithm how to do some task and apply that algorithm to your data. Because actually, when you do programming, you are the creator of algorithms, and you need to write this algorithms that you create by yourself to the computers, to the machines that will follow this algorithm that you specified. So that's why it's never about like just copy pasting. Programming cannot be about copy pasting in general. So try to not think in terms of we need to like what do we need to change to get this work done. Try to think about, okay, I have a task, what I need to do, what manipulations I want to do, how can I decompose the task, and then when you decompose the task, what tools I have to do this operations that I need. Try to think this way, not the way like what I need to change in the code to get the result. Okay. What about others? Do you have problems? Do you have questions?
Should we use heroes or powers to do this?
Which one? Actually depends on data set because I mean.
Yeah, so these three tasks about rows, is it?
I mean, in powers you don't have information about weight, so it's I think pretty straightforward.
Yeah,
because in powers you have only superpowers and name, and that's all. So yeah.
Okay, so these three tasks are about heroes.
Yeah.
Yes.
Yeah.
Okay.
So heroes is something like a meta information, and powers about specific superpowers that they have. Okay, let's continue. So another very actually often and very common task that you might want to do, and you usually do when you do some analysis, you want to sort your rows by some values. So in this case, you have a function, sorry. In this case, you have a function arrange. And it has very straightforward behavior. You just arrange or sort your values in a specific order from the lowest to the largest. And you have NAs in the end of everything. So we start with iron, it's not Iron Man, it's iron, I don't know what. The second is Groot, and so on. The fifth is Yoda, for example. And it goes from the most lightweight superhero to the heaviest one. As simple as that. If you want to change the order, so you want to use decreasing order, use function desc over the selected column. So now it goes from highest value to the lowest value. Sometimes it is useful to combine several columns in a range, especially if you want to several character columns that are like grouping columns, for example, gender. So what do you want to use? You want to arrange all values first by gender. So you put gender first. It will arrange it like first male, then first female, then male, and then NAs. And then after you arrange by gender, inside each gender, you want to arrange by some another variable. For example, by weight. So, for example, you want to arrange first by female, by gender, female, male, NA, and then inside each gender, you want to arrange from the heaviest to the least heavy superhero. Yeah, Giganta is the heaviest female superhero. I mean, it sounds reasonable, right? I don't know her. I'm not so. I mean, I know like Batman. I know Hulk. I know like I know Iron Man and Captain America, and yeah, but not so many of them actually. So please do the task on that, and I think it's all for today, right? Because we are a bit out of time. But let's finish at least with this arrange thing, because at least we learned about what to do with columns and what to do with rows in. But we finish it. Okay, so yeah. Okay, let's do it this way. I will be here for the next 5 minutes, and I can answer your questions about data, about the task, but you can go now. Let's do it this way. So the task is the next about like range. There are just a few tasks. So you can do it now, or you can go and do it at home. Yeah, these tasks I sent you by chat. So yeah, you're free, but I will be here for the next 5 minutes to answer your questions. If you do everything, you can. If you did everything, you can go. If you do everything, you can go, but you can go even now. right? Okay. And I can answer your questions.
Could you show your screen once again?
Okay. Okay.
I will.
Okay. Yep.
So what desk
Desk,
does?
it just changes the order. So without desk, it will arrange from the lowest to the highest. And with desk, it will arrange in the reversed order from the highest to the lowest. And that's all.
Okay.
What do you think about tidyverse? How do you feel about that? Did you hear about that?
I don't know. I think I should personally wait till I get a chance to use it with I don't know, some data that I collected. Yeah, and then I will test it and I will see. But now I'm just getting used to it.
Because in the case you feel like you like lost the line, you didn't catch up at some point. Tidyverse is a good point when you can return, because actually potentially you can work in tidyverse even without knowing base R. Of course, you will do some mistakes. It will lead to some errors that will be hard to resolve if you do not understand base R. And of course, everything that we learned before, if you learned it, will be helpful for you if you work with tidyverse. But actually, you can work in tidyverse without everything like that. So tidyverse did a great job from going from base R to something that is well, pretty beyond base R. I mean, it doesn't change everything. It doesn't change anything in base R. Just use base R things to make working with data very simple, actually, because you have these words for every operation that you do. You need to select columns, you use word select. You need to select rows. If you need to select them just by number, you need slice. If you need to select them by condition, you use filter. For every such operation, you have a word, so don't think in terms of syntax of R structures. You think about operations and what functions you have for them. And usually it works well. Not always, because without understanding the base structure of what happens, it will be something like a trial by error, and it can be long and it can be stressful, I think, at least. For me, it would be stressful without knowing some basic R. But people work with tidyverse without any understanding of R, and they can do some things, and that's really cool, I think. So the main idea of what I say is that if you missed something, it's time to return now, because tidyverse is a great system. It's easy to use, and you don't need much from base R to know to use it effectively. But if you know, it will make you much more effective, of course. Okay, I think that's all for today. If you have any questions about our tidyverse, don't hesitate to ask me. You can write me in Telegram. So yeah. And you have this book that I will translate someday into English, but it will be long stories. So for now, I have only translated some tasks that we do, but in the future I will translate to English. But of course, in English you can find some better solutions maybe than my book. So if you want English materials, I really recommend you the original book for learning tidyverse. It's called R for Data Science. R for Data Science. It is a free book. It was even translated to Russian. But in Russian, the version in Russian is a bit outdated because it was translated almost 2 years ago. So there are many new things now in tidyverse. And it's really great way to learn, because the book, I think this book is the most popular book on R for now. Not even for tidyverse, but for R in general. For today, it's the most popular book ever in R world, and for the reason, because it's excellent. Yeah. But I don't disagree with all approaches they use it there, but it's pretty reasonable. So they start with some data manipulation without explaining what does it mean. And then they introduce some basic features of R in the very end of the book after some complicated manipulations. Okay, so that's all. Bye, everyone.
Thank you. Bye.